Okay, well, good afternoon, everyone. I don't know if anyone's here, so I don't know if anyone can hear me, but I'll assume that you can, unless somebody tells me otherwise. Let's see. Okay, there we go. Okay. Okay, so this is a second video to um, the moles. So here, I think we need to look a bit deeper. We need to look at limiting reagents. So I have some sample questions ready. So let's start with the first one. So the first equation is, we write down our equation, iron solid and sulfur in a liquid form, which is not really important, but gives iron 2 sulfide solid. Okay, so that's our equation. We're told that we have 7.62 grams of iron, and we have 8.67 grams of sulfur, but how much iron 2 sulfide do we produce? So we know this is a limit and reactant type problem because we have two knowns and it's not clear which one to use. Okay, so we are going to try and use both. Okay, because we're not sure which one to use. So we'll do an analysis with the iron, and then we'll do an analysis with the sulfur. In both cases, we want to calculate grams of this chemical. So gram of FeS, gram of FeS. Whenever you write grams of anything, you immediately write it here. And you would write the formula weight of FeS in grams. So for that, we need a periodic table, which I have just slightly off camera. Okay, so I need to calculate this myself. Okay, so Fe, if you look at the periodic table, Fe has a mass of 55.85, and S has a value of 32.07. That has a mass of 87.92. And we set that equal to a mole of FeS. So remember that anything you write as a numerator must be equal to anything you write as a denominator. Now, I've just been told that somebody sent me a message. I'm going to look to see who that might be. Nope. Okay, I don't see any message, so maybe. Okay. All right. Well, I don't see that yet. Okay. Okay, so we have 87.92 grams of FeS is equal to 1 mole of FeS. We cancel mole of FeS and write it here. I know from the balanced chemical equation that 1 mole of FeS is equivalent to 1 mole of Fe. I can't use my input yet, but I know that by definition, 1 mole of Fe is the weight of Fe in grams. So I go back to the periodic table, and I know 1 Fe is 55.85 gram per mole of Fe. Now I can use my input. Okay, so if I run those numbers forward, I have 7.62 multiplied by 1, multiplied by 1, multiplied by 87.92, and then divided by 55.85 equals 11.9, so basically 12. It rounds to 12. 11.995. Okay? All right, we have to do the same with S. So I know that, same again here, 87.92 grams of FeS is equal to 1 mole of FeS. From the balanced chemical equation, I know 1 mole of FeS is equal to 1 mole of S. So I put mole of S up here. In the periodic table, I know that 1 mole of S is equal to its weight in grams. That is 32.07 grams. Now I can use my input. Okay. So I've got 8.67 multiplied by 87.92 and then divided by 32.07. So this is 23.8. This is 23.8 grams. Okay. Now, you've got two possible answers, but only the smallest one actually happens. The smallest value, we said last time, is called the theoretical yield. Theoretical yield is always the smallest of the two values, or however many values you have. The theoretical yield always comes from the limit in reagent. Okay, theoretical yield always comes from the limit in reagent. We have that light phenomenon issue again. I don't know if that's any better. Okay. Okay, so the question then carries on, and it says, oh, actually, this particular question is finished at that point. So this is a nice introductory question, and this one is finished at that point. So I'll put it out to you and see if you have any questions. If you do, you can write in the chat box if you have a question. I am looking out at the chat box to see if anyone has a question. Okay, I still don't see anyone's present, and that's okay. So I guess we'll move on because there won't be any questions. Okay, so I'm going to erase this. We'll look at another question. Okay, so here we have a new equation. So formic acid, 8Q, that just means it's dissolved in water, plus molecular oxygen gives 2 lots or 2 moles of CO2 and 2 lots of water. Okay. The question says we have 3.15 grams of this chemical and we have 2 liter of oxygen. That's unusual. Now we have liters. Okay. The question asks us, what's the volume? So here, X liter of CO2. So this is definitely towards the extreme end of questions. This is a type of question that would use some content that you'll see in the gas chapter that we haven't got to quite yet. But it doesn't really matter. The nice thing about doing it here is it brings your attention to it, and when we eventually do gases, you'll see how these two ideas knit together. Okay, so again, it's another limiting reagent question. Let's try HCHO2. And actually, what I typically do, instead of writing the chemical over and over again, I typically just give the chemical a symbol. So let's call this A. Let's call this B. Let's call this C. Just so I don't have to keep writing the chemical over and over again. So let's look at A, and then we'll look at C separately. Sorry, B. So I want liter of C. Okay, so we're going to write liter of C. Now, here's the thing that you may or may not know yet. Well, this immediate bit you might not know. So it's known that exactly 22.4 liter of a chemical or a gas is exactly 1 mole of the gas. Now this fact is true only at standard temperature and pressure. The standard temperature is 273 Kelvin, And standard pressure is 1 atmospheric pressure. Okay. So 22.4 liter of any gas is equal to 1 mole of that gas. From the balanced equation, I know that 2 moles of C is equal to 1 mole of A. I know that by definition, a mole of A is the weight of A in grams, so I have to add up the weight of all the elements. So let's see what that is. So I've got the weight of, let's see, my calculator. We've got the weight of 2 hydrogens, 1 carbon, and 2 oxygens. So 2 oxygens are 32, and then a carbon is 12.01, and then the 2 hydrogens are 2.02. So this should be 46.03 grams of A. Now I can use my input. Okay, we're going to run this forward. 3.15 by 2 by 22.4 divided by 46.03. Okay, so this is 3.07 liter of carbon. Okay, 3.07 liter of carbon. We're going to do a similar setup with B, and we're looking for the limiting reagent. I know again that 22.4 liter of this chemical is equal to 1 mole of that chemical. I know the relationship between these two. 2 moles of C is equivalent to 1 mole of B. I know again that 1 mole of B is 22.4 liter of B. It's the same idea I had here. It's true for any gas, any ideal gas, under standard temperature and pressure conditions. Now I can use my input. So 2 liter of B goes as my input. So now I can run through the numbers. 2 multiplied by 2 multiplied by 22.4 divided by 22.4. Okay, so this just gives me 4. So as you can see, chemical A gave me a smaller product than B. So chemical A produced the theoretical yield. And that came from the limiting reagent. Okay. Now this question, I think this question goes a little bit further. But no, it doesn't. I've just checked. It doesn't. Okay. I can see that Maria has just joined. Hi, Maria. I hope you can hear and see everything okay. If you need to ask a question, you can use the chat. Maria, I'm actually sending you a message.
Okay.
Oh, hi Maria, I can actually hear you. Okay, I don't have to type it.
Oh, yeah. I opened my microphone too.
Oh, okay. All right, cool. So I don't know if I kind of just saw that you were here when I turned around, so I don't know if you had a chance to look at all of this.
No, no,
Um,
I just opened it.
okay. Then why don't we do a fresh one? So for the benefit of people that have already seen this, let's do a fresh one so that you'll have a chance to see if you have any questions, okay?
Okay. Thank you.
You can look at this if you look at it again. But what we'll do, if more people join, Maria, I'll ask you to mute your microphone again.
Okay.
Okay, so it's okay for now, but if more people join, I'll ask you to mute it. Okay. All right, so the third question, um, let's see. Okay. All right, let's try this one. Let's try 2 and 2H4 plus, let's see, we're told that's a liquid, plus N2O4, and we're told that that's a gas, and that's going to produce 3 lots of N2, and that's a gas, and 4 lots of H2O, and that's a gas. Okay, so what I suggest that you do in an exam, for example, would be to label the chemicals with a letter so you don't have to write them over and over again. So I'm going to call this chemical, I'm going to call it A. I'm going to call this chemical B, this chemical C, and this chemical D. The question gives us some information. It asks us to calculate the volume of nitrogen. So we don't know how many liters of nitrogen. Oh, my computer's telling me I'm on mute. Can everyone still hear me?
I can.
Okay, it must have been you muted. Okay. Um, so we have to calculate liters of N2, and we're given some input. We're told that we have 1,500 kilogram of this chemical, and we're told that we have 1,000 kilogram of this chemical. Okay, so this is called a limit and reagent problem because we have two knowns. So a regular mole calculation or a regular stoichiometric calculation is when you have one known and one unknown. When you have more than one known, it's not clear which one to use. That's a limit and reagent problem. And what you do, you have to use one at a time, and then we'll see what happens when you've done that. So we've got two knowns, so we're going to have two equations. I'm going to have equation A, and then I'm going to have equation B. Liter of C. Okay, so we have liter of C, so I'm going to write liter of C here. And there's a law that we'll cover in class, but we're seeing for the first time now, that says that for any gas, that at least any gas that we see in Chem 65, 22.4 liters of that gas is exactly equal to 1 mole of that gas. So 22.4 liters of chemical C is equal to 1 mole of C. And that's true under standard conditions or STP conditions. And standard temperature is 273 Kelvin, and standard pressure is 1 atmospheric pressure. So we'll assume that's happening here. I have mole of C here, so I write mole of C here. Then I look at the mole ratio. So chemical C, there are 3 moles of chemical C in a ratio with 2 moles of chemical A. So this is a 3 to 2 mole ratio, and that's what we have here. I need to use my input, but I can't use it yet because I have kilogram, but I only have mole over here. So I need to convert mole to kilogram so I can use the input. I know from definition that 1 mole of A is equivalent to the mass of chemical A in units of grams. So I look at my periodic table, grab my calculator. I need to calculate 2 nitrogens plus 4 hydrogens. Notice that we don't look at the coefficient 2. So if you look at your periodic table, nitrogen has a mass of 14.01. So 2 nitrogens are going to be 28.02. And then I have to add 4 hydrogens, which is going to be 4.04 in total. So the entire mass in grams of this chemical is 32.06 grams of chemical A. Okay. But I don't have grams yet. I know that there's 1,000 grams of chemical A in a kilogram of chemical A. So that's my metric table that you would have to know. Now I can write kilograms of chemical A here, and now I can use my input. You multiply all the top numbers and divide by all the bottom numbers. So 1,500 multiplied by 1,000 multiplied by 1 multiplied by 3 multiplied by 22.4. And you divide it by everything on the bottom. So divided by 32.06 and then divided by 2. Okay. So this is going to be a lot of CO2. It's actually going to be a huge number. It's going to be 1.6 by 10, let's see, to the 6th power. So it's 1.6 million liters. We're going to do a similar calculation for B. We can't comment on our results for A yet because we haven't looked at B. Again, 22.4 liter of C is equal to 1 mole of C. The unit here goes here. I know that 3 moles of C is equivalent to only 1 mole of B. So here it's a 3 to 1 mole ratio. I know by definition 1 mole of B is the weight of B in grams. So I need to look at my periodic table and look for the weight of 4 oxygens. 16 multiplied by 4. And then I need to add to it 2 nitrogens, and I know that 2 of those are 28.02. So this should be 92.02 grams of B. And then I've got to convert into kilogram again so I can use it. So 1,000 grams of B is 1 kilogram of B. Now I can use my input, 1,000 kilogram of B. So multiplying through, I've got 1,000 multiplied by 1,000, multiplied by 1, multiplied by 3, multiplied by 22.4. Now I've got to divide that by here. So divided by 92.02. So this is going to be a big number, but not quite as big, 7.3 by 10 to the 5th. So you look at your two numbers and you ask which is the smallest. Well, clearly this is the smallest because its exponent is smaller. So the smaller value always gives you the theoretical yield. Theoretical yield is always produced from the limit and reagent. So I know chemical B was the limit and reagent, and it produced 7.3 by 10 to the 5 liters of chemical C. It did not produce this value because this has got nothing to do with the limit and reagent, and the limit and reagent dominates the reaction. Okay. So we produce 7.3 grams. Now to take this a bit further than the other two examples we've seen in this video, we might ask the following. So an extra question would be if the actual yield is, let's say, if the actual yield is 7.9 by 10 to the 6th liters of C, then what is the percent yield? So we definitely know what the theoretical yield is because that came from the limits and reagents. But the question tells you another yield. It says you have an actual yield of 7.9 by 10 to the 6th. So typically in a Chem 65 class, the actual yield will be given to you. The theoretical yield is what you have to calculate. And then the percent yield, well, the percent yield is the ratio of the two. So the percent yield, sneak it in here. The percent yield is going to be the actual yield, the actual yield. And I've just realized I need to change this because the actual yield is always smaller than the theoretical yield. So I did something wrong. The actual yield is typically given to you, and it's always smaller than the theoretical yield. So the percent yield is the actual yield, so 7.9 by 10 to the 4th, over the theoretical yield as a percentage. So if we do that in this case, so we have 7.9 by 10 to the 4 divided by 7.3 by 10 to the 5 multiplied by 100. We have about 10.8% yield. Why would the chemist want to calculate percent yield? Because he or she might want to know, what am I getting with respect to what can I potentially get? So you potentially could have gotten 7.3 by 10 to the 5 liters. You actually only got 7.9 by 10 to the 4 liters. So you only got about 11% of what you could have got. Or another way to look at that, you are not reaching about 90% of your potential. So a chemist would critique that reaction and say, wow, that's really poor. I can do a lot better. I have 90% waste. That's not good. Okay, so Maria, do you have any questions, or does anyone else have any questions?
Dr. Ross, how
Yeah,
how do I know that the liters are 22.4?
yeah. For now, in Chem 65, it's always going to be 22.4. So it's something called Avogadro's law, or STP, that we'll look at a bit later in the course. It just adds an extra layer of complexity to this question that I thought might be good. So in Chem 65, always assume that 1 liter of a gas is 22.4 liters. Sorry, 1 mole of a gas is always 22.4 liters under STP conditions, standard temperature pressure conditions. So if I give you a question and I say it's a STP, you can always assume a mole is 22.4 liter of gas.
Okay, thank you.
Okay, so if there's no other questions, I'll erase this. And so this is, I think this is maybe the 4th example we've done. So there's a couple of examples before you joined us, Maria. I would like to, in this video, I definitely wanted to hit some percent composition. So I definitely like to erase this and maybe do a couple of percent compositions because we have about 20 minutes left. Okay, so I'm going to erase this. Okay. Okay, so that's a few examples of limiting reagents. If that's insufficient, we can always do more, but there are extra examples on Tyler DeWitt has some videos and Khan Academy has some extra stuff too. So, okay, so percent composition. Percent composition, if you have a compound, let's say a compound has 2 elements, A and B, then the percent of A is going to be A out of A plus B as a percentage. The percent of B is going to be B over A plus B as a percentage. That's the basic equation of percent composition. So having said that, we'll look at a couple of examples now. Okay. So what about, say we have this chemical, CuBr2, and I want to know the percent copper, and I want to know the percent of Br. So copper and bromine. Okay. Okay. It's no good place to put that light. Okay. So first of all, let's see what the mass, the formula mass of this thing is. So I need to add 2 bromine masses together and then add 1 copper mass. So I'm going to get my calculator. So bromine has a mass of 79.90. We'll multiply that by 2, and then add a copper mass, which is 63.55. So the mass of this thing is 223.35 grams per mole. Okay. Okay, so now we're in business. So I know that copper is only 63.55. Out of the whole thing, copper plus 2 of those, which is 223.35. The units are grams per mole in both cases. So the units just cancel, it's a unitless number. And then I multiply that by 100%. So let's do that. So 63.55 divided by 223.55, sorry. 63.55 divided by 223.35 as a percentage, that is 28.5. So just over a quarter of that compound is copper. Now we know therefore that 100% minus that, so we know that 100% minus 28.5 is the percent of Br. So I know what to expect. I can predict the answer, but that's not how you set it up in an exam. So I know it's going to be approximately 73, 72.5, 71.5. But let's show the proper calculation. So bromine, well, I have 2 of them. I've got 2 bromine, and each bromine is 79.9. Out of a total of 223.35 as a percentage. Okay, so 79.9 multiplied by 2 divided by 223.35 by 100%. Okay, the calculator says 71.5. I expected 71.5 anyway, because once I knew copper, I knew the rest had to be Br. So what's left after you take copper away? So I knew what to expect. This is an example of percent composition. So does anyone have any questions about what it is and how you do it? Because you will have to do it on your exam.
So the numbers, we get it from the periodic table, right?
These masses come from the periodic table, correct? And you'll have that in the exam. You'll have that in all of your exams.
Okay.
What's this useful for? It's useful for identifying a compound. So for example, if you have a solid and you're not sure what it is, you could run an elemental percentage composition. So you run that and the data comes back and it says, okay, this chemical has 28.5% copper in it and 71.5% bromine, and that's it. Well, you can convert those masses. We won't show it here because that would definitely be another video if I showed you that. But you could ultimately convert that to moles and look at this mole ratio and see that there's a 1 to 2 mole ratio. So there's 1 copper and 2 bromines. And you could then confirm that this was CuBr2. Where would this be done? In research labs, this would be done. It's also done at the airport. So let's say you're going through passport control and they find a white powder in your bag. And you know it's baby formula, but it might be something illegal. So they take a swab of your bag or the white powder, they go into an office, they run this analysis real quick. They know the elemental percent composition of what illegal substances are and what most common formulas are, and they just want to make sure that what they found in your bag doesn't have the same percent composition as the things on their hit list. This type of analysis could be done in the pharmaceutical industry as well. Let's say that's a contaminant in the synthesis of ibuprofen. So we're looking for the presence of something that has this percent composition in our batch of ibuprofen, and if we find it, we're not going to sell it. So it's a simple calculation. It's used in multi-billion-dollar industries, and for that reason, it's very important. So it's simple, but it's very important. Okay, I'd like to do another couple of examples before we run out of time, though. If you can hear a trumpet in the background, my neighbor's playing the trumpet. Okay, so what about N2S? So I want the percent composition of nitrogen, and I also want the percent composition of S. Okay, so I need to look at the whole first. So I've got 2 nitrogen and 2 sulfur. So I use my periodic table and I add the masses of all those things up. So sulfur has a mass of 32.07. So 2 of those is 64.14. Nitrogen has a mass of 14.01. 2 of those is 28.02. So if we add those together, the total mass of this thing should be 92.16. I've got 2 nitrogen. Each nitrogen is 14.01. 2 nitrogen in a total compound of weight 92.16. So what's that as a percentage? And then sulfur, I have 2 sulfur. The weight of sulfur is 32.07. So 2 sulfur in a compound of mass 92.16 as a percentage. Okay, so looking at nitrogen first, 28.02 divided by 92.16. So this is going to be 30.4%. So just under a third of this compound is nitrogen by weight. 32.07 multiplied by 2 divided by 92.16. So I know that this is 100 minus that. So I know this should be around 70. And the calculator confirms it is 69.6. So they always have to sum up to 100. So they always must sum to 100 because you are the sum of your parts. This chemical is the sum of its nitrogen and sulfur. So our values must be nitrogen and sulfur. Okay. Any questions with this one?
No.
Okay. Okay, we've got about 5 minutes. I think we can do at least one more problem.
Can you do the table salt?
Sorry, say again?
Can you do the sodium chloride?
Yeah, sure. Okay, so this will be our last sample then. So we've got sodium chloride. We want percent sodium. We want percent chlorine or chloride. Okay, so we first get the weight of the whole thing. So we look at our periodic table. We have sodium has a mass of 14.01. Chlorine has a mass of 35.45. So this compound has a mass of 49.46. Sodium is only, sorry, I beg your pardon. That's not right. I used nitrogen instead of sodium. So sorry, sodium is 22.99 and chlorine is 35.45. So this is 58.44. Sodium is 22.99 out of a total of 58.44. As a percentage, that is 39.3%. So I know that this one is going to be 100 minus that, but we have to show our workings for full credit. Chlorine is 35.45 out of a total of 58.44 as a percentage. Yeah, and that's 60.7%. Again, they have to sum up to 100. So although they're in a 1-to-1 mole ratio, they're not in a 1-to-1 mass ratio. And that makes sense because they don't have the same mass. They don't contribute equally to the mass. So although they're in a 1-to-1 mole ratio, it's dominated by Cl minus. Okay. Any final questions? We have about 2 minutes. And as soon as while I'm waiting to see if anyone has a question, the video, as soon as I post the video, it will be available for 14 days, not 10 days actually. Oh, I can see that Wilbur's just joined and he doesn't have a question. Okay. So as soon as I close this conference, I think the video takes a couple of hours to show up on Canvas. They have to render it on the back end. So you won't be able to look at the whole video for a couple of hours, but then it will just show up. You'll know it's available because it will have a view option. Okay. So here are no questions. We'll go ahead and convene this talk. And I think we're doing another talk same time tomorrow, 5 till 6, on a topic that I'll have to look at my phone to remind myself about. So tomorrow, 5 till 6. Oh, predicting charges of ions and predicting formulas of compounds and looking at nomenclature. If that sounds of interest or of use to you, then I'll see you tomorrow.
Okay.
Okay. Bye.